Welcome, everyone. For today's prep, we're going to start to put our first and second derivative tests to use. So we're going to see how we can solve constrained optimization problems. And we're going to look at one example. And this example is going to kind of illustrate the process that we're going to take to solve these problems, these types of problems. All right, so first let's read through what we're going to do here. So we want to find the maximum value of this function q, which is equal to x times y. And we have this additional, what we'll call constraint. We need x plus y to be equal to 2. All right, so we have kind of two equations here. We have the equation that we're trying to find the maximum value for. So we're trying to find the maximum value of this q equation. But then we have some other condition that has to be satisfied for what x and y are doing. So x and y are our two variables here, and we need x plus y to be equal to 2. All right, so we're going to go through the steps to solve these types of problems. Well, we call these constrained optimization problems. Optimization because we're trying to find the maximum or the minimum of some equation, value of something. But it's constrained because x and y can't just be anything. There's some other condition that they have to satisfy. All right, so step one. When we have this type of problem, the first thing we want to do is identify the objective, what we call the objective and the constraint equations. So the objective equation is whatever we want to maximize or minimize. So you're looking for wording in the problem that suggests that. Find the maximum value of, find the minimum value of, things like that. Find the largest, the smallest. So in our case, we want to find the maximum value of this q equation. So this is our objective. Okay, so this is our objective equation. So it's in this case, it's what we want to maximize. So then the constraint is whatever equation or other information that we have that puts some restriction on the variables. So our objective equation here uses x and y. Well, there's this other condition that has to be satisfied. X and y can't be anything. They have to, in this case, if we take x, we add it to y, they have to add up to 2. So that's the constraint in this case. And normally when we're dealing with a constraint, it's the equation that's kind of equal to a constant. Not always, but a lot of times there's some constants involved. All right, so that's the first step. Just make sure you have those two equations all settled in your mind. Then step 2 is we're going to start with our constraint equation, and we're going to solve the constraint equation for one of the variables. So we have two variables here. Solve for one of the variables. So whichever one is easier. So in our case, doesn't really matter. Both are pretty easy, so we'll kind of go with the standard and we'll solve for y. So for our purposes here, we're going to solve for y. But, sometimes you might have a problem where it's easier to solve for x. So we take our constraint equation, and if we subtract x from both sides, we get y. So we get y is equal to 2 minus x. Okay, so that's step 2. Solve the constraint equation for one of the variables, whichever one is easier to do. So then step 3 is we're going to take this value for y now, and we're going to plug it into our objective equation. So the reason why we're doing this is because this objective equation, this is actually a 2-variable equation or 2-variable function. And we only know how to maximize and minimize a 1-variable function. So the next step, step 3, is we're going to take this value for y, plug it in here, and that's going to give us a one variable function. And then we're able to use our standard calculus tricks at that point. So let's see what that would look like. So our constraint or objective equation is x times y, and we're going to replace that value for y with what we just found. So we're going to plug that in, and that's going to give us q is equal to x times 2 minus x. So we're replacing that value for y with what we solved. So the difference, if we look at these, the difference, this version of our function has two different variables. This version of our function has just one variable, x. So we're able to do our calculus stuff with this. All right, so now we have a one variable function, and now we get to the standard optimization techniques that we've done. So we're going to optimize this function. So we're going to find the critical numbers, and then we'll classify the critical numbers. So the usual stuff we've been doing so far. Now to help us with this, we know we're going to find the critical numbers here. So that means we're going to do the first derivative. So we could leave this function like this, but it's going to be easier to differentiate if we actually multiply this out. So let's distribute that x. So if we distribute the x there, we get 2x minus x squared. All right, so this version is going to be easier to differentiate. So let's work with that. So step 4, we're going to optimize. So we're going to first find our critical numbers. And we know that involves our first derivative. So let's get our first derivative. So we'll call it q prime because the function's called q. And let's use this version. So if we differentiate, we get 2 minus 2x. And we know that for critical numbers, we're looking for two things. We're looking for where q prime is equal to 0, or where q prime does not exist. The does not exist part only really happens if we have division. There's no division here, so none. That one we don't see too much, but occasionally it does pop up. And then for the derivative being equal to 0, well, let's set our derivative equal to 0 and solve for x. And we could have factored this, but this is already pretty easy to work with. There's really not too much to factor. So we could just directly solve this for x. And when we do that, we get x equal to 1. So add 2x to both sides and then divide by 2. All right, so that's our critical number. So far, we know something might happen here. So remember, the critical numbers, these are only the possible spots where we have a max or a min. So if we are going to have a max or min, it's going to happen here. But now we need to know, well, what's actually going on there. So once we find our critical numbers, then we want to classify them. And this is where we can use either the first derivative or the second derivative test. And like we've seen, the second derivative test is usually a little bit quicker. So let's use the second derivative test. And whenever we're doing one of these tests, write down the name of the test that you're using. So first derivative test or second derivative test. So write down the name. And like the name suggests, we're going to need the second derivative. So let's calculate q double prime. And we go over to q prime. We want to differentiate again. So derivative of 2 is just going to be 0. And then the derivative of the negative 2x is just negative 2. Okay. So what we find here is that the second derivative is equal to the constant negative 2. So the way our second derivative test works is we take the critical number that we want to classify and we plug it in to our second derivative. So we're plugging x equals 1 into this second derivative. And the way this second derivative works, well, it's always constant. So no matter what you plug into this, you always get out -2. So it's -2. And if we remember our second derivative test, negative second derivative, think of this in terms of the shape of the graph, means concave down. Draw what the concave down shape looks like. And if you draw it, looks like we have a local max. And that's precisely what we have. So we can say we have a local max. And we're not really going to do too many trick questions, but this conclusion here should match up with the original direction. So if we go back up, we wanted to find the maximum of the function, and we just confirmed that the x value that we're getting does indeed give us a maximum. So, so what we've found here agrees with the question. All right, so we're just about there. Last step is we just want to make sure we answer the question. We actually answer the question. So what was the question asking for? Well, it wanted the max value of this function. So we found where that happens. We found the x value when that happens, but we actually want to get the max value of this function. So we just want to make sure we actually answer the question. So the max value of function q is equal to, now we know the x value, when we have the max, and we want to plug that in to our q function. So we could go back to any of these q functions. We could go back to the factored version. We could go back to this multiplied out version. If we did go back to this version, we would need to then figure out also what y is. So let's go back to any of these ones where we've already plugged in for y. So I'll just plug into this. So we're going to take q, and we're going to plug x equals 1 in. And when we do that, we get 2 times 1 minus 1 squared, which is 1. Okay, so that's the max value of q here. All right, so this is the idea. So kind of an easier example here in terms of the calculus part of this. We've done more complicated problems where we've gotten critical numbers and classified them. But now we're going to be kind of putting it together in the context of a larger problem. So usually when we do these constrained optimization problems, this calculus part is not usually the trickiest part. A lot of times it's kind of the stuff that comes before here, just really identifying the two equations and kind of reducing it down to a one variable problem. Okay, so we'll try a few more of these in class. So we'll see you then. Bye-bye.